Welcome to our journey into the fascinating world of rocket science. Have you ever wondered how rockets manage to break free from Earth's gravity and soar into the vastness of space? Today we'll unravel the mysteries behind rocket launches, exploring the science, technology, and engineering that make space travel possible. From the basic principles of motion to the incredible power of rocket engines, we'll guide you through each step of the process. So buckle up as we prepare for liftoff and discover what it really takes to launch a rocket into space. Rocket is a vehicle designed to propel itself by expelling exhaust in the opposite direction. Unlike airplanes, rockets don't rely on air to generate lift. Instead, they carry both fuel and oxidizer, allowing them to operate in the vacuum of space. Rockets come in many shapes and sizes, from small launchers for satellites to massive vehicles that send astronauts to the moon. Understanding what makes a rocket unique is the first step in grasping how these incredible machines work. Fundamental principle behind rocket propulsion is Newton's third law of motion. For every action there is an equal and opposite reaction. When a rocket engine burns fuel, it expels hot gases downward at high speed. In response, the rocket is pushed upward with an equal force. This simple yet powerful law is the reason rockets can lift off from the ground and travel into space, overcoming the pull of gravity. Rockets need a source of energy to launch, and that energy comes from fuel. But burning fuel requires oxygen, which isn't available in space. That's why rockets carry both fuel and an oxidizer. The combination of these two creates a chemical reaction that produces hot gases, which are expelled to generate thrust. Different rockets use different types of fuel, including liquid hydrogen, kerosene, or solid propellants, depending on their mission. Most rockets are built in stages. Each stage contains its own engines and fuel. As the rocket ascends, empty stages are jettisoned to shed weight, allowing the remaining stages to accelerate more efficiently. This multi-stage design is crucial for reaching the high speeds needed to escape Earth's gravity. The final stage usually carries the payload, such as a satellite or spacecraft, into orbit. For liftoff, rockets are assembled and checked on a launch pad. This platform provides support, fueling, and access for engineers to make final adjustments. The launch pad is equipped with safety systems to handle emergencies and withstand the intense forces during ignition. Once everything is ready, the countdown begins and the rocket is prepared for its journey into space. Countdown is a critical phase before launch. Engineers check every system, ensuring the rocket is ready. At 0, the engines ignite, producing a tremendous amount of thrust. The rocket shakes as it overcomes inertia and begins its ascent. This moment marks the transition from preparation to action as the rocket leaves the ground and heads skyward. As the rocket climbs, it must pass through Earth's atmosphere. The lower atmosphere is dense, creating air resistance that the rocket must overcome. As it rises, the air thins, reducing drag and allowing the rocket to accelerate more efficiently. This phase is crucial as the rocket must maintain stability and control while enduring intense forces and vibrations. During ascent, the rocket experiences a point called max Q, where aerodynamic stress is at its highest. This is when the combination of speed and air pressure puts maximum strain on the rocket's structure. Engineers design rockets to withstand this moment, ensuring that the vehicle remains intact and on course. Passing max Q is a major milestone in any launch. Once a stage has used up its fuel, it is separated from the rocket and falls away. This process, called stage separation, reduces weight and allows the next stage to ignite and continue the journey. Each separation is carefully timed and controlled to ensure the rocket stays on its planned trajectory. After passing through the atmosphere and completing stage separations, the rocket finally reaches space. Here, there is no air, so the rocket relies entirely on its onboard fuel and oxidizer. The engines continue to fire, pushing the payload into its intended orbit or on its way to deeper space. To stay in space, a rocket must reach a specific speed and altitude known as orbital velocity. The final stage of the rocket fires its engines to achieve this speed, placing the payload into a stable orbit around Earth. Achieving orbit is a delicate balance between gravity and the rocket's forward motion. Once in orbit, the rocket's main job is done. The payload, which could be a satellite, scientific instrument, or spacecraft, is released. This process is carefully controlled to ensure the payload is placed in the correct position and orientation for its mission. After deployment, the payload begins its journey, whether it's collecting data, relaying communications, or heading to another planet. Rocket engines are marvels of engineering. They work by burning fuel and oxidizer in a combustion chamber, creating hot gases that are expelled through a nozzle. The shape of the nozzle accelerates the gases, producing thrust. There are different types of rocket engines, including liquid, solid, and hybrid, each with unique advantages. Liquid-fueled rockets use separate tanks for fuel and oxidizer, which are mixed and burned as needed. This allows for precise control and even the ability to shut down and restart engines. Solid-fueled rockets, on the other hand, have fuel and oxidizer mixed together in a solid form. They are simpler and more reliable but cannot be turned off once ignited. Guiding a rocket to its destination requires sophisticated control systems. Gyroscopes, accelerometers, and computers constantly monitor the rocket's position and adjust its flight path. Small thrusters or movable engine nozzles help steer the rocket, ensuring it stays on course throughout the launch and into space. Rockets face extreme temperatures during launch and re-entry. Heat shields and special materials protect the rocket and its payload from burning up. Engineers design these systems to withstand the intense heat generated by friction with the atmosphere and the fiery exhaust of the engines. Throughout the launch, rockets send data back to mission control. This telemetry includes information about speed, altitude, engine performance, and more. Reliable communication is essential for monitoring the rocket's health and making real-time decisions during flight. Mission control is the nerve center for any rocket launch. Teams of engineers and scientists monitor every aspect of the mission, ready to respond to any issue. Their expertise and quick thinking are vital for a successful launch and safe operation of the rocket. To leave Earth, a rocket must overcome gravity. This requires reaching escape velocity, the speed needed to break free from Earth's gravitational pull. For our planet, that's about 11.2 kilometers per second. Achieving this speed is one of the main challenges in rocket design. Modern advancements have led to the development of reusable rockets. Instead of being discarded after one use, these rockets can return to Earth, land safely, and be prepared for another flight. This innovation reduces costs and makes space travel more sustainable. Launching a rocket is a complex and risky endeavor. Weather, technical malfunctions, and even tiny errors can jeopardize a mission. Engineers must plan for every possibility, building in redundancies and safety measures to protect the rocket and its payload. Rocket launches can impact the environment, from the release of exhaust gases to the disposal of used rocket stages. Scientists and engineers are working on greener fuels and more sustainable practices to minimize these effects and ensure the future of space exploration. Throughout history, there have been many iconic rocket launches. From the Apollo missions that took humans to the moon to modern launches by private companies, each has pushed the boundaries of what's possible. These milestones inspire new generations to dream of exploring the stars. Space exploration is a global effort. Countries around the world collaborate on rocket launches, sharing technology, knowledge, and resources. International partnerships make ambitious missions like the International Space Station possible and foster peaceful cooperation beyond Earth. The future of rocket technology is bright. Engineers are developing new engines, materials, and designs to make rockets more powerful, efficient, and affordable. Concepts like reusable rockets, space tourism, and missions to Mars are becoming realities, opening up new possibilities for humanity. The principles behind rockets aren't limited to space travel. Everyday technologies from fire extinguishers to jetpacks use similar concepts of thrust and propulsion. Studying rockets helps us understand physics and engineering, inspiring innovations in many fields. Rocket launches capture the imagination of people young and old. They inspire students to pursue careers in science, technology, engineering, and mathematics. By learning about rockets, we encourage curiosity and creativity, fueling the next wave of explorers and inventors. Summary: rockets work by harnessing the power of Newton's third law, burning fuel and oxidizer to generate thrust, and using advanced engineering to overcome gravity and reach space. From the launch pad to orbit, every step is a testament to human ingenuity and determination. Understanding rocket science not only explains how we explore space, but also inspires us to keep pushing the boundaries of what's possible. As we look to the stars, rockets remain our ticket to the universe. With each launch, we take another step toward understanding our place in the cosmos. The science behind rockets is a story of exploration, innovation, and hope for the future. Thank you for joining us on this journey through rocket science. May it inspire you to reach for the stars in your own way.